Thank you.
So, hi, ladies and gentlemen. Today we are going to present to you about how do you fight with high-dimensional, not so small data. This talk is based on our prior experience of working in different companies, big and small ones, and we noticed like some patterns for typical mistakes, and we'd like to share our vision of how do you solve them in a very cost-efficient and efficient performant way. So high-dimensional, not so small data, what is that? And why do you need to fight it? It's very easy to define what is high-dimensional. Well, many of you heard about natural language processing tasks. This is why you have input represented as letters or words. And typically you have millions of different words, and this means if you represent them as one hot encoding, you will get dimensionality more than several million. If you have images, your dimensionality is the number of pixels, which is, again, millions, depends on user resolution. And the problem with this high-dimensional data is that if you take just conventional, generic machine learning algorithm and try to apply it to this sort of data, you will probably fail because it's not intended to be applicable to such sort of input. Not so small is a term which we kind of invented ourselves. You will not find it anywhere in the internet. So yeah, it's kind of our invention. You certainly heard about big data, and not so small data is a sort of big data, but at the same time, you can fit it into a single machine. It's very important, and I'm going to talk about why it's so important to fit your data into a single node. And yeah, let's see why. You can divide your complexity of your problem you're trying to solve as casual or like sort of bleeding edge. This is very, very, very crude classification of all the problems. In our vision, if you have a casual problem, it's well researched and you have a lot of different options and solutions and libraries which you can apply. If it's very bleeding edge, it means that you have a few papers, probably a reference solution, and that's it. And usually academical code is not the best way to apply it into your production. At the same time, if you have little data which fits a single node, you can work with any complexity of your problem. Will it be casual or bleeding edge? It will work. Probably in the bleeding edge case, it will take more time than you want, but you can live with it normally. And if you need to go distributed, well, things are getting harder, especially if you're trying to apply some super bleeding edge algorithm like most recent advance in deep learning generative adversarial network. You will have to write code yourself to make it properly distributed. You'll need to write code to serve the data, and you need to debug a lot of stuff, and yeah, it's going to be intense. Again, how do you estimate if you cannot put your data into a single node or not? Well, first thing to consider is that what type of data do you have? Is it sparse or is it dense? If it's dense, probably you can make it sparse. So I'm not sure how many of you heard about sparse data, sparse matrices. Yeah, of course. So sparse matrices is a way to represent your input as vectors, and they contain a lot of zeros. And since they contain a lot of zeros, you can compress them and put into your operating memory, and everything is fine. So if you try to filter your dense data or eliminate duplicates, probably you can make it sparse and you can live with it. Otherwise, you have to go distributed, of course. Nowadays, from what I've seen recently, the maximum amount of memory you can afford for a reasonable amount of money is about 500 gigabytes. Well, some clouds offer you up to 2 terabytes, but it costs much more money. And yeah, value for money is currently about 5 or 256. So if your data is fitable into this amount, awesome. You just buy a single fat machine with lots of CPUs inside, with this amount of memory, and you're done. At the same time, you need to answer the question, is your data going to grow in the future? If you work with, for example, healthcare data, and your company is not going to invade the market and become #1 player in the whole world, probably no. And you can live just several years happily without your single fat machine, serving your needs as you want. This is another diagram which shows that the previous definition of your problem complexity is actually very crude, and this is more fine definition. It's not mine. I took it from a really nice blog post. It's called Data Science Delusion. You can follow the link on the right down corner. And the blog post says that you have several types of complexity. You have computational complexity, you have complexity of your business domain, and you have complexity of your model. And they're all different. They're all quite different. Business complexity and computational complexity, they are generalized system, and yeah, modeling is your model complexity. Let me give you an example. Suppose that you are solving a sentiment analysis problem, and it's very well known, very well studied. There are a lot of solutions, even startups or companies, having end-to-end solutions to solve this task. If you apply it to, let's say, blog posts which you crawl all over the internet, you are going to end up in the upper left corner because the domain is simple and the model is easy to apply. However, if you are going to apply this model to, let's say, source code, and you want to estimate the sentiment of comments in the source code, whatever, this is not something very well studied. You probably will have to do some specific filtering. You will have to build your custom data retrieval pipeline. So you are going to end up in the upper right corner. And I'm not going to discuss all the corners, just a few words about very hard modeling complexity and very hard system complexity. You should always try to avoid being in this down, right and down corner. It's really hard to tackle this problem. For example, you want to, the thing is, it's so complex that even the fact that you define your problem is a challenge itself. So it's like, I don't know what I want, but I definitely want to try machine learning on this pile of data, and hopefully I will get some good insight of it. So this is like the definition of this corner exactly, especially if you have a lot of data. So yeah, you need to first try to probably solve a different problem, which is easier or with not so much data, and only then transition to this corner because it's very cost inefficient. All right. Again, let's talk about scaling. If you have a single node, the only way to scale is vertical, apparently, and it works perfectly for bleeding edge problems. Actually, it's the only way to scale a bleeding edge problem, because most likely, if you have a paper from academia, they are not going to build a proper distributed solution. It's going to be some proof of concept which works most likely on a single node. And you can just add some more CPUs, add some more memory, and this is the way you work. If you have easy, casual complexity, and you have a lot of data, it's reasonable to scale horizontally. So you have Spark, you have Hadoop, you have Flink, you have other solutions, and this is the way to go. And it's really challenging to scale horizontally on really bleeding edge problems. So you are going to have a dedicated team of engineers working on the problem, coding the solution. Yeah, it's going to cost you a lot of money. Let's consider the case of Netflix. It's a well-known company working in movie and other video types rental. They recently released Vectorflow, which is a native library devoted to vector algebra. Yeah, it actually named after TensorFlow, I guess. It's like trolling or something. So from the ground up, it's sparse aware. It supports sparse data, which means it is operating memory effective. It's I/O agnostic, which means it doesn't impose additional computational complexity. And it works by design on a single machine, which means, they're not going to scale horizontally, only vertically. And this is Netflix. They have a lot of data. Yet still, this is their solution. Apparently, it works good for them. It's a good example. OK. So after we figure out that we should stick to a single node as much as possible, let's answer the question, why do we have to fight with this high-dimensional, not so small data? Probably we don't have to. And depending on your problem, you can apply some sparse-aware algorithm and do not lower your dimensionality at all. If you want to search for approximate nearest neighbors, detect some duplicates, depending on your metric, you can apply SimHash or min-hash algorithms, or you can apply random projections. All of them, as noted here, have really good implementations. Some of them is ours. And if you want exact k-nearest neighbors, there is a really nice open source library from Facebook Research. Okay. It's called PySparNN. It allows you to search for nearest neighbors in sparse representation. It handles really, really high dimensionality, and it works in a reasonable time. If you solve a classification or regression problem, a lot of algorithms support sparse representation and work perfectly with it. SVM from the ground up supports it, and decision trees are designed to handle sparse data too. So step number one is try to apply some algorithm which is sparse friendly. If it's not possible, here is your approaches. Well, since we are engineers, it's a bit technical, and we did our best to generalize these approaches as we could. Principal component analysis and its extension called CUR decomposition are like the first and very probably most well-known ways to reduce the dimensionality. It's like everybody knows it. However, they have some specific, points which we want to discuss. You can apply topic modeling, which is good for explaining your data and explaining your users why you choose option A and not option B, for example. Anything2Ec is a family of algorithms to create embeddings from bag-of-words models and sequential models too. Word2Ec, Node2Ec. Egor is going to talk about it later. DSSM, it's a really nice deep learning implementation from Microsoft Research. So the idea is to create embeddings from all sorts of data, which can be, entangled semantically. So again, Egor will talk about it later. T's and E and large V's are ways to visualize your data, because sometimes to understand how your algorithm performs, you need to visualize your data and visualize the result and see if your dimensionality is reduced in a proper way. OK. Principal component analysis. I'm not going to talk how it works. It's not secret. Instead, the first point which I want to tell is how do you determine the optimal amount of dimensions which you get after the reduction. You should plot the explained variance ratio curve, which says roughly how much of the description stays in your lower dimension space. Most likely, your curve will look like that. It is plotted on fashion-MNIST dataset. Fashion-MNIST dataset is a modern MNIST dataset from Zalando. Instead of handwritten digits, It contains images of different goods, shirts, dresses, and so on and so forth. So most of the implementations provide you this EVR value, and you just look if it's in your allowed range of threshold. Most likely, you will bear with 5% decrease. In this case, this means about 400 on 200 dimensions. PCA involves centering the columns of your input matrix. Of course, it can work with sparse matrices, but after centering, you will end up with a completely dense matrix. If your sparse matrix is very large, your dense matrix will be even larger, and it will not fit into operating memory, and you will fail to calculate your PCA. This is always something which you have to keep in mind. Your output is never sparse too, by design. So if you lower your dimensions, let's say 2 times, and you can still end up with a really, really huge dense matrix. So it's not, unfortunately, applicable in all the cases. As you see on the image, if you do not center your data and just apply truncated SVD instead of full cone PCA, your first principal component will be not the component you would like to have. So it just points to the mean of all your data points, and you can calculate it yourself. It's not a big deal. If you center your data, your first principal component is always the right one. If your data is extremely sparse, the mean value of every column will be very, very close to 0. And in this case, you can just bypass this centering step and just apply a truncated SVD. In NLP, it's called latent semantic analysis. In this way, in this case, it will probably work for you. Principal component analysis is vulnerable to outliers. This means that even a single outlier, as on this image, you have a single outlier over here, it reduces the quality of your PCA considerably. In this case, your first component rotates with a really considerable angle, and if I'm not mistaken, it reduces the quality for, let's say, 15%. And this is 100 dots. So 1% of outliers means 15% decrease of your accuracy, which is really huge. The solution is rather simple. You just filter outliers or apply some damping function, for example, logarithm, to eliminate this sort of thing. I mentioned truncated SVD earlier. Truncated SVD is the algorithm behind PCA, and it just has all the properties which I just described. It handles sparse input, but output is never sparse, and so on and so forth. There are 2 proven implementations which we personally worked with. The first is Phoebe PCA. Well, we are Python engineers, so all the libraries which we recommend, they are Python friendly. So Phoebe PCA is a Python implementation of randomized truncated SVD from Facebook Research. And the second is just sklearn, which delegates all the powerlifting to underlying native libraries. CUR decomposition is one step towards sparse friendliness in a way that it generates sparse output. Of course, the quality of your dimensionality reduction will be less. At the same time, since it's sparse, it will be possible as whole. So you should consider CUR instead of truncated SVD as the underlying engine of your PCA. Finally, before passing to Egor, I'd like to stop on topic modeling. The idea behind topic modeling is that you have a series of sets, and you want to determine frequent subsets in your sequence of sets. For example, you have documents. Documents have words, and you want to mine topics from your documents. A topic is a list of keywords, probably with ranks, which describe some specific property of your document. For example, you have documents about literature, about art, about science, about sports, so on and so forth. And each this entity has a list of keywords which allows you to decide on this topic. And usually you apply, if you're a Python developer, you apply, how is it called? GenSim, yeah, of course, GenSim. Rather production-ready library works great, sometimes rather slow, unfortunately. And the second implementation is not so well known. It's called BigERTM. It also has a Python wrapper, but since it's written in C++, it is much more effective in terms of vertical scaling, and it allows you to perform topic modeling up to 50 times faster than GenSim on the same hardware. People always confuse topics and clusters. Topics after topic model are not your clusters. And if you pick all your documents related to sports, it's not a cluster of documents. It's just some property which unites all these documents. If you want to group your documents in topic space, you need to apparently cluster them using k-means or any other clustering algorithm. At the same time, if you are solving a problem like eliminating duplicates or finding documents which are similar to each other, like contain copy-paste from each other, pretty common task if you do some web analysis, I guess. Topic modeling is not good for solving your problem, but it's good for explaining your users that you solved it. The thing is, if you have two documents which are 2/3 art and 1/3 science, it doesn't mean that they are close to each other and they are similar. It just means that the topics are similar, and this is quite different. If you want to determine copy-paste, you need to apply some other model, some black box, a neural network, whatever. And after that, when you present your results to your end user, it just shows that, OK, topics are similar, so that's why we think that the documents are similar. Egor, it's your turn.
Thank you, Vadim. So, in this part of presentation, I'm going to talk mostly about embeddings and a bit about recommender system and visualization. Why embeddings are so popular in now time? Because they're extremely useful for processing sequential data. And we live in the world of sequential data like text, system logs, messages, and so on. I have a question. Who works with some kind of sequential data?
It's a very broad definition.
Yeah, but still. So you can find this part quite useful for you, and maybe others will find how to apply this even for your job. So I will explain embeddings on Texto data because it's like most natural data that everybody understands. And even Texto data, it has some important properties that we have to be aware of. One of these properties is that number of unique words grows linearly with the size of corpus. So there is no saturation, like somebody may expect that we have only some limited number of words, because people tend to invent new words. For example, you have iPhone, and then somebody say iChair, or something like this. But the point is that even with this huge number of unique words, you can try to reduce the complexity of your data set with some simple preprocessing techniques, for example, stemming. And as you can see at this plot, it allows, for example, to reduce the number of unique words by 20% just applying stemming. Another important point that you have to keep in mind is that Texto data usually have a lot of duplicates. So this data set, it's called Usenet. It's a data set of news articles. And news agencies, as you know, they like to copy-paste articles from another news agencies. So like with some minor modifications. So, and as you understand, usually this copy-paste, this almost identical samples, they give nothing to your algorithm. It's better to eliminate them. According to our experience, one of the very useful technique is called min hash. Well, Vadim mentioned it some time ago. So in our case, it allowed to reduce data set from 13 million samples to 9 million samples. Like you can imagine that it will work like 50% faster, all next steps. So always keep in mind filtering the data. Okay, what is embeddings? Embeddings is distributed representations of item in feature space. What does it mean, distributed representations? For example, in case of one-hot encoding, you have only one value that represents this item in huge feature vector. In case of distributed representation, each item, some kind of meaning of this item is distributed among many different features. So what are the desired properties of embeddings that we want to achieve? It should be low dimensional. For example, several hundreds instead of millions with one-hot encoding. Another property, like similar words, should be located close to each other in the feature space. This property gives us like another property that we can try to use. We can search for analogies. Like you have word king, you may find some similar words with similar meaning. Another property is based on vector algebra, that each point it's a vector, and if you apply some vector tricks, you can try to receive some unexpected results. It's a very popular example that embedding for woman minus embedding for man is approximately this equal to the embedding of queen minus embedding for king. So it's some kind of reasoning that you can try to extract from embeddings. The first model that allows us to achieve these properties, I'm going to explain you about skipgrams, how it works. This model, for example, let's use example. MCube is a great conference. So on input of this model, we provide target word. On output of this model, we expect to receive context word. So in this case, it will be like input is MCube and output is a great conference. The properties of this model. It works well even with small data set. Sometimes we have small data set. Another important property is that it represents well even rare words. And I think this property is very important because in text dataset, the distribution has a long tail. So it has a long tail distribution of word frequencies. Most of the words, they are quite rare. And if you cannot make good embeddings for rare words, probably your embeddings will not be so good. Another model, continuous bag of words. It was the first model that was introduced when word2vec appeared. It works in opposite way. On input, it expects the context. On output, it expects the target word. So using previous example, on input we will have is a great conference, and expected output will be MCube. What are the properties of this model? It's faster than skipgram model. Sometimes it's important. And it has better accuracy for frequent words. So for example, if you have not so many unique words, it's better to apply SIBO model. And again, without good implementation, ideas worth not so much. And in case of word2vec, Facebook with fast text shines. So it's extremely good embedding agent for words and sentences. So it has several important features. It can compute embeddings even for unseen words using a subword embedding trick. So what does it mean? It means that when you calculate embeddings not only for words itself, but for parts of words too. And when you meet some new word that you have never met before during the training process, using this part of words that are quite frequent, you can somehow estimate the embedding for unseen word. Another feature of this library is that it allows you to make classification of text. And the last one, it allows you to compress the model. For example, if you want to make fast inference step, to make fast predictions during application, so it's very important to compress your model as much as possible. Next thing that with compressed model, sometimes you can deploy it maybe even to some small device like mobile phones. Embeddings are not limited by word-to-vec approach. There is another approach based on global vectors. This approach combines advantages of two major model families: global matrix factorization and local context window, word-to-vec. Here it is an example how it works. So we have sentence text with 5 unique words and window size equal to 2. And we build concurrence matrix. The rows is target words, columns is context. Blue squares, it's zeros, and orange square is non-zero values. So, and again, without good implementation, idea worth not so much. In this particular case, Swivel from Google works really well. So it's embedding engine that works on concurrence matrices. It is like Glove from Stanford, but it works better, as they claim in Google. So we forked the TensorFlow implementation and improved it a bit, so you can find it by this link. What are the features of this embedding engine? So it has multi-GPU support. In case if you have some fat instance with many GPUs, it's very good for you. Then it scales with vocabulary size. Previous solutions, word-to-vec, they scales with the size of corpus. So, for example, if you have petabytes of data, probably you cannot apply word-to-vec because it will take forever to finish the training. Next thing that it has efficient sharding algorithm to distribute workload. So you can notice it here that each small shard that will be distributed to worker, it tries to preserve the global distribution. Okay, let's make some intermediate conclusion. When you have moderate size dataset, like up to several hundred gigabytes, and you don't need to preserve, you just need to preserve several millions of unique words, your natural choice is continuous bag-of-word model. When you want to preserve many millions of unique words with the same size of dataset, your choice is skip-gram model, because it helps you to fight with long-tail distribution of word frequencies. When you have really huge dataset, like many hundred gigabytes, petabytes of data, word-to-vec models became unapplicable, and you have to scale with the number of unique words instead of the size of the document, the size of the data set. And here you have to apply Swivel. If you have not so many millions of unique words, Swivel works well. The worst case, when you have many millions of unique words and your size of data set is really huge, it's bad luck. So none of these approaches will allow you to make experiments fast. So somehow you have to reduce either number of unique words or data set itself. Okay, next area that I want to talk about is graph embeddings. It's non-linear data, like opposite to linear data in text. We have sequence of data, and this non-sequential data. It's important area for almost every company, because we are surrounded by social graphs, dependency graphs, and so on. And we want to embed nodes in this graph. It could be you, people, or something like this. And this embeddings, it should preserve the same properties as we had for word-to-vec embeddings. Like nodes with similar context should be located close to each other. There are many different approaches. I'm going to talk about one of them called not-to-vec. So it has just several steps, but it's better to explain them on some visualization. So we have some graph. And the first step of this algorithm is that we start random walks at this graph. So we pick up some node at this graph and start to traverse this graph according to some logic. This traversing of graph will give us sequence of nodes. Then you start these random walks many times, so you receive many sequences of nodes, and then you can treat sequences of nodes as sequences of words, and you can try to embed them. And you will receive embedding for nodes in your graph. Okay, I have to mention couple of libraries from Facebook because they are extremely useful for almost any task that I describe. First one is star space. So the name itself, it's like star space. It tries to embed everything. So it computes embedding for word, sentences, documents, even for graphs. It's like fast text, but next version. So it allows you to make text classification, even ranking, and even more, it allows you to make collaborative filtering and content-based recommendation. Another library, it's called FAIS. It's a library for k-nearest neighborhood search. So it's like the next step after you compute embeddings for anything you want to compute. So you have to make some search queries to find similar words, to find similar users or something like this. And in this case, FAIS shines. Okay, next topic that I want to cover is content-based recommendation system. Whenever you want to make personalized services like some item recommendation, movie recommendation, advertisements, even search engines, you have to work with recommendation and ranking approaches. Why don't I explain about collaborative filtering? Because it has several problems. First one is called start problem. If you don't have data for your service, so you cannot work with it. Next one, that usually if you have new items in your, new products in your service, usually it may require from you to recompute the model, to retrain the model. And it doesn't work really well with really huge matrices. But there is an approach that allows to overcome such limitations. I will explain you about deep semantic similarity model from Microsoft. So I will just use explanation from their article, how it works. So it's an example of a search engine where you have some queries, and you have to provide a list of documents related to this query. So on the input of this model, you have, so it's model with two inputs. First one is query itself, second one is document. First layer is bag of words layer. So they used 500,000 unique words to represent queries and document. Next layer, they apply some trick to reduce dimensionality because multiplication of high dimensional vector to some embeddings, it's quite expensive. So they apply trick to reduce dimensionality. They extract n-grams, character n-grams from words. How it's done? So they have, they augment each word with start and end character. And after this, they split this word into character n-grams and apply hashing trick. And as a result, they receive 30K unique values. After this, they start to extract deep representation of these features, first layer, second layer, last hidden layer. So it's another kind of embeddings. And using these embeddings, they try to calculate how similar these items using cosinus similarity. It's not the only approach that you can use for content-based recommendation. There is an example from Russian Google called Yandex. They applied a similar model, but augment it with bigrams of words, and they use more unique words, and it works in real time for like millions of users in Russia. Okay, so how can we understand, how can we evaluate our embeddings? So without good visualization, it's hard to understand that your algorithm converges well based only a loss function, because it's not really informative. So as you remember, in case of embeddings, we have properties that similar items, they are located close to each other. So I'm back. They are located close to each other, and usually they can be located on some complex manifold. And as you understand, distance preservation is not enough to reduce the dimensionality. That's why TSNE was introduced. Name itself, T-stochastic neighborhood embedding, makes sense that it should preserve the neighborhood of each sample in the data set. So it respects the relation between distances, but not the exact values. So it has a very good blog post at DistillPub that you can find at this link. Let's go further. So next algorithm is large width. Somebody may even call it like TSNE on steroids. It's a large-scale TSNE replacement from Microsoft. It works in several steps. So you have a data set of your feature vectors. For each sample, you try to find several nearest neighbors. So using this information, you build the graph. And then using like this, this step loses some information, but it's still okay. It works really well. Then using this graph, you just make visualization of millions of points, and it gives you a sense how like your samples are located in feature space. Okay, let's go to conclusion.
So to conclude, let me just repeat what I just said earlier. You should always fit your data into a single node. To do that, probably you will need to reduce the amount of your data, and you should try a sparse-friendly model to not even, going further with dimensionality reduction. You should always eliminate outliers. They're usually very bad for any sort of algorithm, not only principal component analysis. And usually PCA is a good first step for any other algorithms which require kind of lowered dimensionality.
So yes, and in many cases, you can try to embed your samples into some low-dimensional feature representation space. And according to what I explained, it's possible in many cases, text data, graph information, like some content-based recommendations and so on. And don't forget, to understand if your algorithm really converges, you have to visualize it early. And it will give you some kind of sense. If, for example, you see that similar items are not located close to each other, probably even if your loss function is small, something is wrong, and you have to investigate.
So this is our context. Thank you, and we wish you to win the battle.